Okay, let's get started. Hi everyone. Thank you guys for coming. My name is Mingmin Chen. I'm a software engineer with streaming data team at Uber. Today, I will talk about how we build reliable redeliveries and data queues with Apache Kafka. So, for some of you who don't know what Uber is basically a ride-sharing, food delivery, and transportation network company. And so basically, Uber provides service to move people and things in real time. As you may imagine, Uber has a lot of use cases that need to move data in real time. That's where a messaging system comes into the picture. And it plays a very significant role in this case. So as in the first item in today's agenda, I will talk about some of our use cases and our scale of messaging system at Uber that we built on top of Apache Kafka. So some of the use cases include like rider-driver matching, fraud detection, trip processing, and so on. Then we will talk about what motivates us to build reliable redeliveries and data queues on top of Apache Kafka. Then I will talk about some of the high-level design and architecture for this feature that we are building. At the very end, I will talk about some of the future work on our roadmap. All right. So let's talk about some of the use cases and our scale. The very first use case is real-time driver-rider matching. So when you open Uber app to request a ride, that request actually goes through our messaging system on Kafka. And the data is delivered to the downstream streaming processing system. And on the other end, we have driver app that's sending the supply data to the downstream system as well via Kafka. With both demand and supply data, the downstream system will do the driver-rider match. So that data will be sent back to the rider app together with the ETA. The data will also send back to the driver app, such that the driver partner will see like you are being matched with a rider. The second use case is providing real-time ETAs for Uber Eats. Uber Eats is actually one of my favorite apps. For those of you who don't know Uber Eats, it's available in Poland and many other countries in the world. It's super awesome. If you haven't tried it out, just try it out. It's super awesome. So compared to the rider-driver matching, providing real-time ETAs for Uber Eats is even harder because it involves three parties: restaurants, eaters, and carriers. So we need all of the data from the three parties, and underneath we have machine learning platform to compute and predict the ETAs for the food that you order on Uber Eats. As you can see on the app, when you click the order button, it will show up the ETAs. Of course, the ETAs will adjust based on real-time traffic and the restaurant itself. There are a bunch of other use cases that use our messaging system, including fraud detection. So basically, like if there's fraud, we have downstream system that will detect in real time. You can also share your ETAs with your friends or family to notify them, where you are and when you arrive at your destination. When driver partners and writers sign up, those data will also go through our messaging system to downstream. And exactly, there are a bunch of other use cases. So in summary, Kafka is being used at Uber for many use cases. So here I list 5 different categories. The first one is being used as general pub/sub and messaging queue. Secondly, as I mentioned in the previous example, those are for like streaming processing. We have our own in-house self-servicing platform, which we call it Athena X, which is built on top of open source Apache Samza and Flink. It's very simple to use this platform. People can just write a SQL query and point the data source and the sink, and it will just do it will create the processing job and run it for you. The third category is database changelog transportation. So all the database changelogs will be transported to Kafka via Kafka to the downstream system. At Uber, we have many database systems. The first one is Schemaless, which is a NoSQL database that we built on top of MySQL in-house. We are also using Cassandra and MySQL, and all of the changelogs are transported via Kafka. The fourth use case is data ingestion. It's actually a very typical use case for Kafka. So all the data that needs to go to Hadoop and HDFS the data will be transported to via Kafka. Also, some of the data need to be backed up in S3, and that is also so producer need to produce to Kafka, and we have downstream system to back it up in S3. Last but not least, Kafka is being used in the logging for different applications and services. The logs will go through Kafka to Elk to Elasticsearch. People can search their logs and debug. It's super useful. So here is the data infra architecture at Uber. As you can see, on the left-hand side, we have so many data producers. For example, rider app, driver app, and different kinds of APIs and services, etc. The data will produce to Kafka. And as I mentioned, databases, the changelog is also transported, is also produced to Kafka. On the right-hand side, we have different kinds of consumers. Like as a general pub/sub use case, we have downstream services that is consuming directly from Kafka. We have search, which is a service that calculates the search multiplier, and we will use it to calculate the fares, and the fares will be show up on the mobile app. We have Elk, as I mentioned, for logging use cases. The data will be ingested to Elasticsearch. Developers can create their own dashboard, and then they can do debugging. It's super useful. And we also have our streaming processing frameworks. People can do like real-time analytics and create alerts and dashboard on their own. Ingestion, data go through S3 and also to Hadoop for batch processing. All right, so let's talk about scales. This is actually my favorite slide. So we are serving tens of thousands of topics in our Kafka clusters, which contribute to trillions of messages per day. And that's tens of petabytes of data per day. And all of these numbers are excluding replications. All right, So let's talk about what motivates us to build reliable redeliveries and delete queue on top of Kafka. All right, so there are two categories of messaging. The first one is streaming, and second one is queuing. For streaming, it means the messages need to be ordered in some way, and the consumers for different consumer group need to be exclusive, meaning like consuming in one consumer group should be isolated with other consumer group. The data is usually partitioned, and partitions are assigned to different workers. And it's usually providing like commit up to API to keep track of the progress for consumers. For queuing, the match is usually unordered, and the match is shared among different consumers. So if a message is consumer in one consumer, that message should not be delivered to other consumer. And usually, it needs nack support. Think of like RabbitMQ, ActiveMQ, or Amazon SQS. So let's look at what acknowledge model that Kafka provides. So in a typical Kafka topic, it usually contains like multiple partitions. And a partition, from consumer point of view, a partition is usually assigned to one worker exclusively. And the message is delivered in order. Consumers can only commit the offset to this assigned partition. Offset is a unique ID for each individual message in this partition. So we are keeping track of a pointer for the progress of the consumer. But why is commit up to not insufficient? It's insufficient for the queuing case. For example, trip processing. Like think of a message representing a trip in a Kafka topic. When we are processing a trip, like the downstream system may have some issue. For example, HTTP endpoint may have some issue. And in this case, we don't want to block processing of the next message. We want to nack the message and have it redeliver back. And then in this case, it should be non-blocking. We also have some other queuing use cases. For example, emails and push notification. In this case, like ordering is really not a requirement, and commit up to will be blocking for the processing. So we need to build our own redeliveries and delete queue feature on top of Kafka. One of the questions that people may ask is, why do we build on top of Kafka? There are a bunch of other options out there. The first one is KMQ. KMQ is something that a startup built on top of Kafka. KMQ stands for Kafka Message Queue. It supports nack, out-of-order nack. We can also use RabbitMQ or ActiveMQ, and also Apache Kafka, which natively supports nack on the consumer side. Or the last option is build yet another messaging system, messaging queue from ground up. But why do we build on top of Kafka? There are a bunch of reasons. So first of all, Kafka is widely used at Uber. It's well known for its reliability and its performance, like providing very low latency for the producer and consumer side, and very high throughput. Last reason is it's very cost efficient, because we are already operating Kafka in a very large scale, and we already know Kafka very well. We don't want to invest too much engineering resources to another matching system, it's not a good idea for the resource itself. So that's why we built the reliable redeliveries and delete queue on top of Kafka. So when we build this, there are a bunch of requirements that we need to fulfill for the future. First one is, of course, nack, and also redelivery. So when a message is nacked, it needs to be redelivered back to the consumer. In case there is a downstream issue for the processing, for the message processing, we need to provide some kind of delay between the redeliveries to make sure that we don't hammer the downstream system, and we can make sure a proper delay to make sure the retries will hopefully be success. We need to provide delete queue support. So in case there is a poison pill message in the topic, we need to put it somewhere. People can inspect the message in delete queue, and then choose to do about it. People can do purge, meaning I don't want this message in the delete queue. I can do merge, meaning I can reconsume back those messages in delete queue. Like for example, if there's a downstream system issue, like all the retry failed, but then when the downstream recovers, we need to reprocess those messages. So in this case, we need to be able to merge those messages back. Uber is running multiple data centers. So we need to support cross data center failover. In case like a data center is failover to the other, we need to be able to provide a mechanism to resume the consumer from the other data center. At Uber, we are using different programming languages, including Golang, Java, and Python. So we need to provide clients in different languages for this feature. So let's recap the acknowledgement model that Kafka provides. So you can only commit up to this offset. So to provide the nack feature, that's how we do it. So let's look at one particular partition in this case. Suppose this partition is assigned to this particular consumer process. So the message is delivered to this process in order. Within this consumer process, it may want to spawn multiple thread workers to process the messages. To keep track of the progress for different workers and for out-of-order nack, we need to provide an in-flight offset checker within the process itself. So in this case, we have like a in-memory in-flight offset checker for the partitions that is assigned to this process. All right. So all the workers will report the progress or nack to the in-flight offset checker. All right. So let's zoom into this in-flight offset checker and see how it works internally. Suppose last time it commit to offset 3, and now we resume the consumer from offset 3. Let's see how it works. So message of offset 3 will be assigned to one of the worker, in this case, worker 1. 453 is assigned to worker 234, in this case. And for each individual message, we'll put a timer for the message. Now say worker 4 finish the processing of message 5, and then acknowledge the message back to the offset checker. So that message will be marked as green in this case. And then messages of offset 7 will be assigned to worker 4 to continue the processing. Worker 3 now finished message 4, and it will be marked as green, and then message 8 will be assigned to worker 3 and start the timer, of course. Now, worker 1 nack the message, or if it times out, we mark this message as red in this case. But what do we do for the offset checkpoint? We cannot simply just commit offset 5 to Kafka. We should make sure we do properly for offset 3, such that we don't lose this message. We need to provide at least once guarantee, and we also want to minimize the duplicate. If say we only commit offset 3, and then now we restart the consumer, like message 4 and 5 will be redelivered. But that's not what we want, because 4 and 5 are already acknowledged. We don't want to redeliver these 2 messages back to the consumer. So what we do in this case is we will have a separate topic for this particular consumer group. And the naming convention is simply the topic name, underscore, underscore, the consumer group name, underscore, underscore, retry. And the message itself for the nack message or the timeout message will be produced back to this separate topic. With that, and this producing will be act equals or, meaning like it guarantees the delivery to the retry topic. Now, in-flight offset checker can commit the offset 6 back to the original topic and continue the processing. So what do we do for the message that was produced to the retry topic? So that's what how the redelivery works. For the consumer process, it will reconsume the message from the retry topic. So, and we also put the retry count in the message header to indicate how many times it has been retried. How do we achieve the delays between the retries? So in addition to the retry in the metadata, we also put timestamp in the message itself. So when the consumer consumes the message back from the retry, we check the timestamp in the retry message and see if it fulfills the delay requirement. If not, it will sleep and make sure it has the sufficient delay in between the delays. After a message reach some retry count, like the max retry count, the message will be redelivered back to another separate topic, which is the dialect queue topic, which has the same similar naming convention. And the message will be put in this special topic. So people can just do like inspection. We have tooling for the users to inspect what's there, and they can check whether it's a message that I want to reprocess, or it's something that is like a bad message that I just want to discard. So people can choose to purge the message in the DRQ, and we provide self-servicing tools that people can just purge the message in this particular topic. So it will not. So by purging, like the message will be not redelivered back to the consumer process. People may choose to merge the message in the dialect queue topic. In this case, we will mirror the message. We'll replicate the data to the retry, and then reset the retry count to 0, such that it's like the first time it's being processed. All right. So with that, we have already fulfilled 5 requirements. so far. Nack, redelivery, delays between redeliveries, delete queue, and delete queue purge and merge. Next feature we want to support is cross data center failover. So here is a simple version of a Kafka setup at Uber. We are running in multiple data centers. And usually data is produced to the regional Kafka cluster within this data center. And the data will be replicated to aggregate cluster within this data center. So we are using uReplicator, which is our in-house version of MirrorMaker. We have, by the way, we have already open source uReplicator. And I will include a link at the very end for uReplicator. So data from multiple data centers will be replicated to the aggregate Kafka cluster via uReplicator. So aggregate Kafka cluster will have a global view. You have all the data from different data centers. uReplicator is also responsible to produce the offset mapping between the regional Kafka cluster and the aggregate Kafka cluster, and then produce the map, and then it will put the offset mapping to our offset sync service, and that is very useful for the failover support. So suppose there's no failover. One of the data center will be chosen to be the active data center. In this case, the consumer application within this data center, in this case it's DC1, will be active. And all the messages will be delivered to the consumer application from the aggregate Kafka cluster within DC1 in this case. And the consumer application in the other DC will be passive. So basically we have library within our consumer library to check which DC is active in the current moment. And if it's passive, then it will basically stop the consuming from Kafka cluster. So what happens in case there is a failover? So DC1 becomes passive, and DC2 becomes active. To make sure consumer application in DC2 consume starting from the right checkpoint, the first thing we need to do is for the offset sync service to seek the offset from DC1. So basically, we are getting the offset from DC1, and then max back to the original Kafka cluster offset in DC1 and DC2, and use these two offsets to map the offset back to the aggregate Kafka cluster in DC2. With that, we will minimize the duplication for the newly active consumer in DC2. And we also guarantee at least once, meaning like consumer will not lose any of the message that is not being processed. After the offset sync, the new active consumer application will start consuming from the aggregate Kafka cluster, and in this case, supposedly the duplication will be minimized. With that, we achieve cross data center failover. Last one is we need to provide clients in different languages. All right, so here is what API looks like in Golang. So I highlight a couple of things here. So as you can see, people can just put a subscription with a handler, and that handler is just a function with the context and the byte array for the message. So it's very simple for user to use it, because they can just put their own business logic within this handler and don't worry about like redelivery or deletery, etc. And then people can put the config as in the second parameter in this case. People can put what kind of topic I'm subscribing, and what kind of or active strategy that I want to use. Like we provide different kind of strategy. Like active passive is one that I just mentioned before. That is a good one for cross DC failover. We also support like all active local, meaning like people would just want to consume data from local data center, and people can choose whatever like or active strategy that you want to use. And they can also specify concurrency. In this case, we are setting 100 concurrency 100, meaning that we will spawn 100 thread within the consumer application itself. So people can specify like a proper in case the processing itself is very heavy or very slow. In this case, they want to set up like higher concurrency to make sure it can catch up with the message rate from the producer side. People can also set timeout for their handler. So for this timeout, in case a handler doesn't return within the timeout, we will drop the processing, and we will produce the match back to the retry topic, and then reconsume for the next retry. I think one thing that is missing is the delay. So people can also set delay between the redeliveries. And it's actually super easy for people to write their consumer application using our API that we provide. And we also provide logins and metrics for people to check the progress or any logs from their handler. And we also monitor like the offset, see how much is backlogged, how many messages are being nacked, how many of them are timeout. So people can check a bunch of things using our own dashboard that we create for them. So it makes sure like it's super easy for people to use and debug. And we also provide similar API in other languages, Java and Python. So people can just do their own handler, and it's they don't need to worry about other things. So with that, we fulfill the programming language requirement. All right. So the last item I want to discuss is the future work on our roadmap. Of course, we have been doing some good features. We want to open source this feature back to the open source community. We have already open sourced the APIs, the retry and delete queue feature in Golang. We haven't open sourced the handler API yet, but that's something we want to do in the future. We are working closely with the open source community to make sure, like all of the things that we build on top of Kafka can be used by other users of Kafka. Another thing we want to do is provide better self-servicing. We have already provided a bunch of toolings and monitoring logins for people to do their work, but there is still room that we can improve for self-servicing. Last one is serverless. We are working closely with our sister team to provide serverless support. So basically, people can just register a handler, and then all the deployments, and then like a fanout, like in case like it's too slow and the backlog is too high. In this case, the serverless framework will do the fanout by itself. So basically, it means for the developers, the only thing that they need to do is write a handler, and that's it. It's very, very simple. And that's also something we are actively working on to support our internal users. Here are a bunch of links to some of the things that we mentioned in the previous slides. First one is a GitHub repo for our Go library, which provides the nack or redelivery and dilated queue support. Second link is actually an engineering blog that was written by one of the users. It's actually a very common pattern that people want reliable redelivery. And now we are providing this feature to all of our users, that they don't need to rebuild this feature on their own. The third link is to our repo, to a GitHub repo for uReplicator. As I mentioned, it's an in-house version of uReplicator, of MirrorMaker. I'm sorry. Last one is the engineering blog for uReplicator. In case you are interested, just check it out. All right. With that, concludes my talk. So we have more open source projects that you can find out in eng.uber.com. And thank you for your attention. By the way, Uber is hiring. Thank you.